quote this one. Okay. So look at this data set. The data set has been taken from the Kaggle. It's called the graduate admission data. Admission data is the data set. See, GRE score, TOEFL score, and university rating, ranking, or statement of purpose, letter of recommendation, cumulative GPA, research, whether you have a research or not, chance of admit. See, so the GRE, normally everyone has to do it, the GRE, if you're going to enter into like a graduate school, but the TOEFL, you don't have to do it. Some students who are international students, they have to take this one. Test of English for English as a foreign language. TOEFL or test of English as a second language. Some people, some countries, they have to do TOEFL. Okay, this one TOEFL, they pronounce like a TOEFL. This one university ranking, statement of purpose, that has to be written by you and say why you really want to pursue in a graduate studies in that particular area of a specialization, and the letter of recommendation coming from your whoever for your referees and your cumulative GPA, and whether you have done research or not. As an undergraduate, whether you have done research or not, what's the chance of admit? Okay, but this is the data set. By looking at this data set, let's see that what we are trying to achieve over here. This data set contains several parameters which are considered important during the application for master's program. The parameters include the GRE, graduate record examination. There are two types of GREs, one in English, one in language, sorry, one in English and the other one in that particular subject. Okay, and the TOEFL, as I said earlier, TOEFL university rating out of 5, this one out of 340, this out of 120, statement of purpose and letter of recommendation strength out of 5, undergraduate GP out of 10, research experience either 0 or 1, chance of admit. And this is the acknowledgement, inspiration, and citation. See, this is the person that put forward this one at that particular conference. So let's see, for each of the following explanatory variable, these are the explanatory variable, one at a time: research experience, undergraduate GPA, GRE, TOEFL score. Fit a separate regression and correlation for the outcome variable. Chance of admit would be your response variable. This is why will be explained by one at a time. Sometimes research experience. It's a categorical. If it is categorical, how could you gonna do that one? If it is undergraduate GPA, quantitative. See? This one, quantitative. This one again, quantitative. See, like that. Okay. So this one, and then fill in the following cell with the appropriate value for each element of the model. So you have a correlation coefficient R, capital R, we mentioned about that. Now B naught, you know, intercept, B1 slope, degrees of freedom for model. There are several types of degrees of freedom for total, degrees of freedom for model or regression, degrees of freedom of error. And that's pretty much similar fashion. We have sum of squared for 3 types of sum of squared. Sum of squared model, sum of squared model or regression, sum of squared error, sum of squared total, but here we are asking you to put just the model only. Then sum of squared total. This one. Again, we were looking for sum of squared total here, pre here, and F here, F value. Okay, interpret the values. Look at when interpreting a correlation between two quantitative variables. If you have a y and x, both are quantitative, do not indicate that the coefficient is positive or negative. Rather, use a description of the variable involved, like the greater distance from home is associated with more commutating time. See, the higher the value of GPA, the higher the chance, like that. The higher the value of GPA, the higher the chance of get admitted to the the graduate school. Like that kind of description, rather than just go with the rather than quantifying that one. See, you're going to qualify that, but rather than quantify. Rather than quantify means like that. Just simply put the number, and then you can say they were highly correlated or not, like that. But rather than talking like that, they want to write something in that in this way. See, describe that relationship. See? When interpreting a correlation between a categorical and quantitative, definitely quantitative comes all the time because the y variable is quantitative. See, This means there's a other variable is quantitative or either quantitative or categorical. See, X variable. Here, X variable quantitative, you have to do not indicate the coefficient in positive or negative. Rather, use a description of the variable involved, like those who were in romantic relationship tended to have a more absences from the school than those who were not in romantic relationship. Related to this one, we have only one categorical explanatory variable, research experience. See, research experience will be utilized in order to explain the chance of admit. This is a quantitative. Quantitative versus research experience is categorical. Quantitative versus quantitative. Quantitative versus quantitative. Quantitative versus quantitative. So is that the case? You have to write like this. So you can say that those who have that research experience tended to have a more chance of being admitted to the graduate school than those who were not exposed to the research when they were doing undergraduate, like that. That's kind of a description you have to write rather than just simply put the number and put the negative value. Then when it comes to the B1, slope for quantitative explanatory variable. Quantitative explanatory variable, describe whether the outcome variable is let's say that for instance, this one is undergraduate GPA, quantitative, and describe whether the outcome variable also quantitative. Okay, interpreting B1, it's definitely quantitative. Outcome variable is the chance of admit expected to increase or decrease, and by how much for each unit change in the explanatory variable. See? By changing like a 1 unit in the GPA, how that the chance of admit gonna change. That's the B1 that's the slope. But if you interpret in B1 for categorical explanatory variable, describe whether there is a mean difference, direction and amount in the outcome variable between the group coded 0 and the group coded 1. Use the name for the groups. You must know the coding. So you can say people with the research experience would be your categorical explanatory variable. In that case, you can say the people without research experience, you can code that can be coded with 0, and people with research experience can be coded with 1. So then you can say that there's a mean difference in the outcome variable, mean difference in the chance of admit for the between the group coded with the between the group with the without experience of research and with experience of research, like that. You can write like that. When interpreting B note for quantitative explanatory variable, describe what is the expected outcome when the explanatory variable is 0. See, when the GPA is 0, what would be the chance of admitted? That's a quantitative explanatory variable, GPA. So when GPA is 0, how come? But if it is a categorical explanatory variable, describe what is the expected outcome for those who have predicted score of 0. That means you can simply say categorical explanatory variable is chance of research experience. You can say that expected outcome. Expected outcome means the average, okay? Expected outcome is the average. Average outcome, average chance of admitted for those who have no experience in research is B naught. Okay, like that. Okay, so that it depends on that what are they have selected 2 of them. You don't have to do this one for all of them. What they have selected 2 explanatory variables, which one is categorical, the other one is quantitative. You know, if you quantitative, how it would be. And in addition to that one, pre should be even explained. Okay, pre is nothing but that the proportional of reduction in error, how much error being reduced due to that particular model. Okay, then which model is the best according to PRE, which model is the best according to F ratio, which model is explained the more variation per degrees of freedom. Like that, later on obtain prediction for the following respondent for each of the explanatory variable below. Based on the analysis, we do analysis. Who do you believe has the best chance of getting admitted? Why? Respondent 40, respondent 56, respondent. For the best model that predicts the outcome variable per degrees of freedom, edit the following equation. In this a regression equation. Okay. And this is not the model, this is a regression equation. See? If you get this part only, that's the model. That's the model. Right there. And then what do you make prediction with this one? Okay. You're gonna put that input, take the inputted values that you would use to make prediction with this one. Extract input the value those subscripted by I in the model equation for the respondent I, the 100th one into the equation you edited in P7. So you need R. R you can remember. R is the measure of the strength between X and Y. That's the measure of, okay, measure of strength. You saw that one last time. You can remember that. Okay, we talk about the beam. R is a correlation coefficient. That's the square root of the determination coefficient. See, it's the square root of 3. See, 3 is the R squared actually. P is the R squared. If you know the correlation coefficient, how to get the PR, proportional reduction in error. It's nothing but that square in this one. We mentioned about one. And we went a little bit further down and then we were talking about how to get the R in different ways. See, how to get the R. You can get the R by running COR. You can get the R. R means like a correlation coefficient, okay? Excuse me, COR test or B1 of the standardized model. Standardized model is nothing but you're going to standardize X and Y by taking C-score like this, and then fitting into the model. That model, if you go ahead and looking into its slope, that slope is nothing but the correlation coefficient. Okay. When we talking about in regression, there are two major parts. Looking for an association. Sorry, here an association. Association or relationship between X and Y. That's been expressed by the regression equation. See, this is Y equals write this one to add something here. So here, this is population version. It's a sample version. Okay. Population version, you can say Y equals beta naught plus beta 1 X plus epsilon. Here, Y equals B naught plus B1 X plus E. Y equals B naught plus B1 X plus E. That's how they differ from each other. Okay. So, as I mentioned, B naught would be a good estimate of beta naught. B1 would be good estimate of B1, beta 1. And E would be good estimate of epsilon. Okay. So this part we call the model, population model. This part we call the sample model. See, this part, okay, if I get this one here, only this part, we're gonna say expected value of y. See, it's called the expected value of y. Expected value of y. You're gonna write like that. But in sample, if you go ahead and look at that part, b naught plus bx, you can call that one y hat. Y hat, yeah, call the estimated y. See, the difference. So you have a, in sample version, you call y hat. In population version, you call ey. Ey is just like a model part. See, it's a model, this part. And this is the part we're going to draw into a regression line. Draw into a regression line means what? This one, see? Can remember. See? If I draw this one, both this is a population version. The population version is a sample version. Sample version, you have a data, see, scattered all over the place like this. Here you have y here, you have x here. You have x, you have a y. See, now you're gonna find this line. See, this line that's gonna go through the center. See, this is the center. This is x bar. This is y bar. See, that's the center. See, go through the center. That equation you're gonna write, that's the model. Y hat equals b naught plus b1 x. Equation of the line. Equation of the best line. Regression line. In a similar fashion, we're gonna think for a given x. Let's say in our example, given height, we think in population we have infinitely many thumb lengths. See? Infinitely many thumb lengths. If you have like that, that will be definitely modeled by a distribution like that. And it has its center here. See? The center is, I'm going to call that one mu. See? In a similar fashion, that for the, if you go to the next one, you have the same infinitely many, not only one point, see, like that. And if you keep doing that one for all these, later on this mean value will be, connected by that one. See? Means. See? The means. Those are the populations. See, they are bell-shaped. We're gonna assume those are bell-shaped. They are center. We're gonna find like an equation going through this one. That's why I call this one. See, Ey equals beta naught plus beta 1x. Or you can call that one mu as well. See, that's the equation of the line that passes through the centers of all distributions. Distribution, normal distribution. See? Normal distribution. They've been shifted. See? These distributions, they have a spread. Look at these distribution have a spread. This spread, if the spread of all distributions are the same, we're going to call that one homoscedastic. If not, we're going to call heteroscedastic. Okay. So you can see that on the version and population version, we're going to write like that. Okay. So, and the correlation, the same thing. Correlation here, the same thing. See, they will see how they were connected. Their strength of measure given by R here given by rho. Okay, So you have to understand that one. That most everything coming from the sample are all statistics. Okay, on the other side, those are statistics. Those are estimated value. These are estimated value, estimated value, estimated value, estimated, 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 estimated. All these have their counterpart in population version R, beta node, beta 1. This one also have. Okay, we're not going to talk about that one. This one also, this is supposed to be not pre, supposed to be the pre hat. If also put with the hat, but we don't put the hat, we're going to just simply go with the F pre like that. But these are going with the three different symbols. See, here beta node, here B node, here beta 1, here B1. Okay. Yeah, then let's see that this one here. Let's try to answer this one. Okay, let's try to answer one by one. Yeah, already we have. See, okay. Let's go ahead and get this one. Okay, my data. Set this one my directory, and let's read the data. Admission data CSV. Same thing that I showed you earlier. And get there. Let's look at the first few 10 entries. Okay. Then you can install these packages. Supernova will give you for the full ANOVA table, B node, B1, pre, etc. And the GG formula, you know, that can give the GG functions, every function used in graphs. And the mosaic for the correlation test, and the descriptive statistics. So those three packages will provide different types of functions. Okay, before that one, let's see this one string. 400 observation, 9 variables, including this one, 1, 2, 3, 4, 5, 6, 7, 8, plus the serial number 9. They are the type of they are variable, integers, numeric. They call the numeric for that decimal one. If they were discrete one, or if they were like with the just the numbers without any decimal, integers. But they everything belongs to 100 per watt. That this one, even the integers, you know, this is a categorical. See, 1 and 0, 1 and 0, categorical. Okay. So let's go ahead and see this one, the research experience, yes or no, question 1. Okay. Let's convert this one to that 0, 1. I'm going to convert into what? Recode to whatever you have, 0 to be no, 1 to be yes. Okay. Let's see. Oops. Okay. We need this one to be installed. Let's install this one. Okay, try to get all these three. No. One more library, mosaic. Yeah, good. Okay, string, okay, links, that's the same thing. Okay, okay, let's look at the recode. And go to data. See, now yes, I call that one research factor 1. Okay, to do either this way or this way, using recode or factor. We use the factor, see, research factor. I'm going to call that one research factor and put it back into my data frame. Okay, you can do this way. I call that a research factor. Still, you can do like that. Instead of going for 0, 1, I want to distinguish that one from that other quantitative variable and say, hey, this is the only that categorical variable we have in this particular data set. Okay, so I did like that. Okay, then a little bit graphical representation of the chance of admit versus research. So these are the three few things that they're going to research: undergraduate GPA, GRE, TOEFL. Okay, research experience, say chance of admit versus research experience. Chance of admit versus undergraduate GP. See, this one versus GRE, this one versus TOEFL. Okay, GPA, GRE, TOEFL, and research experience. Okay, so let's have a look at it that if you want. Okay, but the graphical representation of chance of admit versus research. See, quantitative to categorical. And you can go first one, faceted histogram of chance of admit by research. Like that, you can change with the people with the research experience versus people without experience, how they distinguish from each other. Like that. Or you can compare and contrast this one with the research experience, sorry, the research of, sorry, I'm sorry, the explored by, what's this? No, box plot. So grammar chance of admit. It's not right. Chance of admit by research. Box plot of chance of admit by research. Box plot by research. See, yes, see. Chance of admit, see. Chance of admit, and then two categories. I could get a chance. Method one, correlation coefficient using z-scores. So I'm going to get that, go to data, go to the chance of admit. I'm going to convert this one to z. I'm going to call that one z chance of admit. And I'm going to look into this few of that. See? These are the chance of when we convert it into standardized, when that particular variable chance of admit has been standardized. These are the entries now. Pretty much similar fashion, I'm going to do that one, same for the research as well. See? Standardized. Then I'm going to run the regression between the standardized ones. See? Z chance of admit versus C research with the data. And I'm going to call that one Z research underscore regression. Okay, let's run this one. See, these are the values. And from this one, you can easily say it's B1. B1 is this one. Okay, this B1, this B naught. You know that one. Okay, or you can say slope of that particular one is you're going to find the B1 from this guy. B1, or you can read from here. Easily read from here. That's nothing but 0.05532. Okay, now 5.532 to the times 10 to the minus 1. Oops, okay, that's okay. I'm going to run again. See, 0.553202, that's the same thing. 0.55, sorry, 0.5532, 0.5532. See, that's the slope. Slope is taken as the correlation coefficient. It's a one method of doing that. Second method, you can easily go to chance of admit, research data is data, method is Pearson correlation coefficient. I'm going to call that one research correlation. It's another way to have a look at it. Same name I'm going to utilize, but yeah, under the see, we still get the same value, 0.5532021. And let's go to method 3. You don't have to do all the methods, but you better off learn all these methods. It's going to be very helpful, very useful. Now you're going to go to code-test, code.test function. You're going to write everything in the same way. You don't have to run lm inside, okay? Just simply write the y and x and separated by tilde. See? Still I call the research correlation. Same thing. You see, co is this one. This is the confidence interval. We mentioned the confidence interval. You are not interested in only the point estimate, you need a whole bunch of estimates, and you need a test. See, you're going to talk about that one down the road. We can see alternative hypothesis, true correlation is not equal to zero. See, true correlation is not equal to zero. What that means, what they're trying to say over there in that this whole description. Hmm? Can show you something. Test. Run the test. So the p-value has been given that one. Should be a little bit picture. Okay. Would like to little bit talk about that one, just a little bit. To this one. Sorry, this one. So see these values, see p value, see degrees of freedom, p value. Where are these coming from? See, when you run the test, they say here alternate hypothesis is true, correlation is not equal to zero. What that means? True correlation, true one. This is not the true one. We don't have the true one. That's the problem. True correlation not equal to zero. See, it's not equal to zero. So here, see, they say that null hypothesis. That's I think null one. Okay? Null one. Null hypothesis for it. True correlation equal to zero versus HA alternative hypothesis. I mentioned the other time. Okay. True correlation. True correlation not equal to zero. That's what they were talking about. See, that means H naught rho equals zero versus its counterpart HA rho not equals zero. See, rho, we're gonna say rho, can you remember? Then if you have that one, you really need, see, you know, that's if you have a like this not equal sign, you're gonna call this one a two-tail test. Two-tail test. Why? Because of this not equal sign. Two-tail test. If you have a two-tail test, you really need the test statistic. Test statistic to run the test. They say that one is nothing but T is nothing but okay R n minus 2 divided by 1 minus R squared. R squared. See, n minus 2 is nothing but, you know, n minus 2 in this case is nothing but, I'll write this one, R degrees of freedom of error. You know that one. 1 minus R squared. See? 1 minus R squared. See? If you plug in R, which is, see, R you have already 0.55, sorry, I'm going to go back to this one. SR. See, 0.5532, see, 0.5532, 0.5532. I'm going to write this one. 32, okay, times degrees of freedom in minus n is how much? 400 minus 2. See, that's the one they show over here. See, 398. 398. We are trying to get this t value. Okay. 5532 divided by square root 1 minus 0.5532 square. Punch this number into calculator and see whether we're going to get the same answer. 0.5532 times square root 398 divided by square root 1 minus 0.5532 square equals 13.24. 13.24. 13.24. See, 13.24. That's the t value. That's how you get the t value from that. 13.24. 24. That's the same value. That's the same value we get over here. Now, with this one, how could we gonna make a conclusion? Then you need the p value now. How do you get the p value? They think this one is okay. I'm gonna write something here. This tilde means is distributed. Okay, is distributed. With what they think t where t distribution. Okay, I'm gonna write with the degrees of freedom of error. I'm gonna get this one here. I'm talking about this one, DDFT. T distribution. It's another form of normal distribution with degrees of freedom. Freedom. How much? DFT, which is n minus 2, which is 398 in our case. See, that distribution is how it looks like. It's the same thing like the normal distribution. It's another derivation of the normal distribution. Only difference, see, there's a degrees of freedom. See, so degrees of freedom of this one is 398. It has a center at 0. This is t distribution. This is the t distribution. Then you're going to go ahead and locate the value that you got over there. I'm going to call this one t, capital T, which is 13.24. T, 13.24 here, and negative t, which is negative 13.24, because it's a two-tailed test. See? These are the rejection region. Those are called rejection region. These two, they are symmetric. Okay, rejection region. Rejection region. Then we're going to find p value. P value is nothing but probability. T value, t distribution. T distribution is t greater than t naught. T greater than t. T greater than capital T. And two of them, double it. I'm going to double both sides. 2 probability t greater than 13.24. Okay, 13.24. How do you find that? See, 13.34. Okay. So if you want this one, you can say 2 times pt. See, probability of t distribution in R. Or you can get that one in probability of t distribution. Okay. So that one t distribution, when you put the 13.24 and degrees of freedom 398, that will give you that. That's how you get the 0, 0. It's almost 0, 0.00. The PT, that's the R code. Probability of T distribution greater than this one, 13.24, 398. Okay, actually that should be, I'm gonna put this one, okay, -1 for my convenience, because we are taking the area to the left, okay. Area to the left, I'm calculating this area and double it rather than calculating this one. Calculating this area, I'm calculating this area and double it, still 0. That's how you get 0. That's the p-value. That's how you p-value. Then how do you make a conclusion? Conclusion come, decision rules say, okay, decision rule, I'm going to write here decision rule. Decision criteria or rule, reject H0 if p-value is extremely small or it is less than the level of significance. It's alpha 0.05. And by looking at this one, see, you can say since p-value is 0, we reject H0 and infer that the true correlation is not equal to 0. That means there's a correlation between, and you can write that one in the context of what's being given in the chance of admit, and then whatever that research experience or whatever the variable you can trusted in. Based on that one, you can write that one. Since p-value is 0, we reject H0 and infer that the true correlation is not equal to 0. So that means you reject this one. See? And then your claim is right. Whatever you claim is right. That's the idea over here. That's why you get this one. See? That's the whole thing. The confidence interval, you can write that a different way. The confidence interval is like a different process, but I gave a rough idea for this one. You can, when we going through the confidence interval again, we can come back and then visit this one. Okay. So see, so then the method correlation coefficient I got from the core test, and then I'm using the supernova. See, I'm gonna go to this one. I'm gonna run that regression between those two variables, get this one, and then I'm gonna run the supernova on that guy. See, and go to the pre. See, and go to the pre. From the research regression, you can recall, rather than put the numbers, don't put the number. Ask the machine to go and read this value rather than you put the number. That's the whole purpose of using the programming. You're going to say, hey, I need the pre-value. So you know 0.3060. You don't put the 0.3060 and find the square root on that. You know the square root of pre is nothing but the correlation. We talk about that on the other day. See, we talk about that one. Can you remember? We talk about that one. See? Correlation coefficient is nothing but square root of the determination of coefficient, which is R squared or proportional reduction in error. Okay, so you can find that way too. See, square root, that was, sorry, that one, supernova. See, oh sorry, this one, yeah, that I have set up that one for that by putting that one too. But you don't have to. Okay, this one is not necessary, but I'm showing that one that is already over there, plus that I have put over here to show that it's easy to get that way. But this is the proper way of getting that one, rather than putting the numbers. You don't have to put the number. Okay, then pre. I'm gonna run that one more time. Okay, if it doesn't work, then take the square root on that one, 3, which is 0.5532. or I'm going to go ahead and get the ANOVA, okay, not the supernova, ANOVA table for that regression, ANOVA. And then I'm going to call that one ANOVA.table. See, look at it is missing what? The last part for the total. That's okay. I really need what? I really need to go to the ANOVA. I'm going to go to the research and get the sum of square, which is research sum of square is how much? 2.4833. See, I'm going to assign that one to A. See, let's say A. See, and the other one, I need the sum of square error. Go to residual. It's like a matrix. Go to this row and go to this column. Go to this row and go to this column, sum of squared column, which is 5.6313. And then you run the and then what I'm gonna do, pre is nothing but sum of squared regression divided by the total sum of squared regression. I'm gonna add these two to get the total. See? You can get the pre like that. 30 again. You get that pre and then find the square root on that one. That would also gonna give you the same answer. So similar fashion, you can do the same thing for all of these, but you don't have to. But I'm showing you several methods over here. See, 5 methods, 4 methods, like 4, 5 methods to get the same thing done. But if you simply use the core, that's more than enough. If you simply use the core test, it's more than enough to get the correlation to fill this up. See, correlation between research and chance of admission. Between chance of admitting undergraduate, and then you're going to do this one for all these explanatory variables. See? Then I do the same thing for what? See? Now I'm using the GPA. See? GPA. For that one, first I looking into something like the graphical representation. See? See? This time you get the GF point, okay? GF point. See? Scatter plot, because this time you don't have what? You don't have a categorical data. See, it's not categorical data. You earlier you got the faceted histogram because you have a categorical data. Okay, you had a box plot given by that categorical data. You can show that one, but this time we don't do like that because these both are quantitative. Okay, I'm gonna go to GF point. See, scatter or jitter. If you want, you can use the jitter. And LM, GFLM, see, open close will give you the fitted line. Okay, GF underscore LM give you the fitted line. This is the best line. You see, it's been already programmed. It will select the best line. That's gonna go through all these points plus the center. Center should be somewhere here. Okay, so you get the idea. Then you're gonna, as I do earlier, you're gonna convert explanatory variable as well as a response variable into Z or standardize both of them. See, that one, then you're going to run the regression between those standardized variables. See? Then get that one. It's okay. B1 is referred to as the correlation coefficient. See? If you go ahead and recall B1 from that guy, it is the CGPA correlation. See, that's the same thing. 8.733 times 10 to the negative 1 is same as 0.83. I just this one in another method using core, the Pearson. You can find that one too. See, same thing. In core test, see, same thing. Okay. You can see. And using supernova. See, supernova using that one. And then go ahead and read the super pre-value put to this one and find the square root on that one, or ask that machine to go and read it. That's the most proper way of that, and find the square root on that one. And with the one line, you're going to run 2 times if it doesn't count. And the same way that I did earlier, that reading, see, reading from run ANOVA. Okay. Oops. Oops. GPA regression. I'm sorry. That's the GPA regression. CGPA. CGPA regression. Okay. Then that one. And then you get the sum of squared regression, sum of squared total, and you create the P, A divided by A plus P, sum of squared regression divided by sum of squared total, go to pre, and from pre you get the correlation, which is the square root of that. Same thing in different way. So you can pretty much similar fashion you can do for the GRE score as well as too. You don't have to use all this method, but I did. Yeah, see, and see later on, then you can do the same thing for the TOEFL as well. Okay, see, just pick one of the methods and have a look at it. See, for the 80 point something. And if you have it just for the GRE regression, then now you have a TOEFL. Even for the TOEFL, let's go to call this one. 6.79 like that. See, like that. PR is same as R squared. See, PR is same as R squared. See, TOEFL correlation squared is that one. So now you're gonna explain that one. Research experience. Those who have R research experience coded one have a higher chance of admit compared to those who do not have research experience with this much of a strength. B naught. It's B naught. The expected chance of admit for those who do not have a research experience is this much. B1. We already found those things. You can, when we run the regression, you can get that one. The expected chance of admit for those who have research experience is do not have the proportion of variation in student chance of admit explained by whether they have research experience or not is this much. See, explained by whether they have a research experience or not is that much. In a similar fashion, you can write for the GRE the same thing under the question 2. See, we have picked only 2 of them. See the description. For all this you can fill out, okay, because you know that when you have F, see these parts, not only R, B naught, B1, all these already here at a certain point. See, let's say that let's stick to that. I'm gonna go back to the first one. You got the R, let's say that I got R, then I have that research, okay, research experience. I'm gonna get R by running this one, okay, test 0.55. You can put that value. Now I need the rest of them. See, if you run 3 of these together to get the supernova table, that will have pretty much everything that we are eyeing for. See, you have a B naught, sorry, B naught. You don't have a B naught. In order to get the B naught, I'm gonna here, sorry, here, see, B naught we have. B naught I have, B1 I have, sum of squared model, no, see? Sum of squared model, see? Sum of squared model, sum of squared error, sum of squared total, all these you have, see? Sum of squared model, sum of squared total. Let's look at this way. See? I need degrees of freedom for model. Sorry. Degrees of freedom model is 1, you know. Model sum of squared is 2.483. See, we put here. Sum of squared total is 8.115. We put here. PRE 0.3060. We put here. F value we have already 175.514. The similar fashion you can do the, while you are in the process of finding that the R you can see we found it, or you, if you're not going to go through all these methods, just simply that run the regression and get this value, plus that running that co test, get the R value. Okay, and then only two of them are given over here to be given their description. So see, this is for the research experience and GRE scores. See, those are the ones we were talking about here. After all these been calculated, see, this is for the research experience R B0 B1 PRE. R B0 B1 PRE. Again, GRE score as an explanatory value R B0 B1 PRE. So we have the R, you have to just not simply put the R value, just rather than that, and those can say those who have a research experience coded one have higher chance of admit. Higher chance of admit compared to those who do not have a research experience, which is B naught. The expected or chance of admit for those who do not. Expected means average chance of admit for those who do not have a research experience, which is coded as 0 is 0.6. B1, the expected mean or the expected or the chance, the average chance of admit for those who have research experience is this much higher than those who do not. You can say like that rather than talking about the difference. Okay. And the proportion of variation of students' chance of admit explained by whether they have research or experience or not is this much. So similar fashion, when you get the GRE as your explanatory variable, you can talk about that one. Then the number three, we're going to ask that which model would be the best model. Out of all the models, when you run, go to the model with the highest PRE. Highest PRE, you can see which one has the highest PRE when you run everything. So the cumulative GPA is the one that which has the highest PRE. And the similar fashion, highest F. They both higher the value of that one, the better the model would be. Okay, so that's why they ask which model would be the better model. Okay. Which model is the best or the better, okay, according to F ratio, according to PRE. Which model explain more variation per degrees of freedom? What do you mean by the more variation? More variation per degrees of freedom means what? They are looking for what? Sum of squared error explained by the model per degrees of freedom. That means mean squared regression. MSR, okay, per degrees of freedom. So which model explain more variation per degrees of freedom? See, more variation is error. See, sum of squared error. Sum of squared error B per degrees of freedom means mean squared error. Which models will explain the mean squared error? Explain, okay? Whichever the model explain more variation per degrees of freedom is taken as the best model. Here again, CGPA, I noticed that one, but you have to run all of these for the ANOVA table and then compare and contrast and then see which one has that one, okay? Okay, then number six, they are looking for something to that. Number five, number six, obtain the prediction for these respondents. Their respondents is research experience, undergraduate GPA, GRE, TOEFL score. See, respondent 14, respondent 56, respondent based on this model, this model, this model, this model. So they are looking for what? The predicted value for the chance of admit, Y hat. They're looking for Y hat. Y hat, when research experience has been explained, has been utilized in order to explain the chance of admit for the 40th respondent, 56 respondent, 78 respondent, 93 respondent. So that's why we're going to make a function here. So this is the regression. I'm going to run regression, see, and then I'm going to call the research regression. I'm going to make a function of that one. So every time I put the value here, that I can go to the make function and put the value in, I can get the my necessary answer. Okay, whatever the answer that I'm looking for, I can easily say. Let's say I'm going to work on this one. Okay, let's go to this one. In a similar fashion, you can do the same thing for the CGP, GRE score, TOEFL score, right there. Make sure you're going to type in that, type in as it is, okay, exactly the way that how it's been given in the data set. So then I'm going to go to my data, respondent 40. I'm going to say, I'm going to go to the data and go to the 40th person and I pick his research. See, research, because this has been based on the research. See? In the research experience, I need the 14th person research experience to be plugging into the formula. 14 persons, because you know the formula. You know the formula. You know this one. You know this one. Okay, look at this one. See, 0.6377, 0.5083. See, chance of, let's say that one for this one. Yes. See here. Let's go to one regression line, one regression chance of admit. See, this is, you're gonna say chance of admit. This is chance of admit. Because B0 plus B1 times, then this X should be research experience. See? Research experience. Okay. Since I'm interested only in the have this one, the model, I go with this one enough. I don't need the error term. That means we are looking for y hat B0 plus B1 X. Okay, then I'm gonna a little bit modify this one. See, for that particular person, then I'm looking for the y hat for the 40th person, B0 plus B1. 40th person research value has to be put it over there, whether he has a research or not. See, X of the 40th person, research experience, whether he has a research experience or not. B0 value, already we know that 0.63, 6340, I'm sorry, 6377 plus 0.6377. I'm going to show this one to one of them, then you can get the idea what's going on. See, plus P1 is 0.1583 times this 40th person value. This is my head. 40th person, if you go to the 40th person on this, the data set, see, this research, okay, H column, okay. The 40th means 41st because the first entry has been allocated for this one. This is the 40th person's research. See, no research. See? Yeah. No research. I got the 41st one because the first row has been allocated for the titles. Okay, so the see 0, but we don't go and read that one. His real value is 0.48. See, this is a real value. This is y. This is y. It's not y hat. Okay. Go to the 41st person, y hat. This is y. I'm in for y hat. I'm in for y hat. I know that one. That's the one I'm trying to calculate. In order to get that one, see, in order to get that one, see, I already set up this one to a function. If I know the research value for that function, see, I built up the function for that research regression. It's called the research function. I'm going to go to that one, and then I'm going to say A would be that 40th person research value, which is 0. See, you can go ahead and see this. This one, A is how much? 0. See, you're going to put that into that whole thing, whole formula. That means I'm going to put this into this formula. Y hat 40 is 0.6377 plus 0.1583 times 0. See, that's the same thing going to happen here. Then if I put that into that function and then run it, sorry. Oops. Search function. So please search. Okay, I'm going to go back to here. Okay, good. Research form. Okay, go here. A 6.6376. 0.6376. 7677. Why here? Because decimals being taken out. See here, they've been rounded. I went with what being rounded already, but it's gonna show you if you go to this calculation. If there's calculation, they don't do the intermediate, the rounding. Here I pick this one. It's already been rounded. Yeah, see, 63.76 has been rounded to 63.77. So you're gonna get that one. That's the one that rather than doing by hand, you got this one. But we know that, see, but we know that y of the 40th person is how much chance of admit? We know that one. We know that, see, 0.48. See, 0.48. 48. See, that's the true value. Then the gap is called the error. See, an error of the 40th person, see, would be what? Y40 minus y hat 40, 0.48 minus 0.6377. Point 0.48 minus negative 1577. That's the error. This is the error. Error or residual related to the 40th person. We can calculate that one too. We don't do by hand. We can even calculate that one. That's the 40th person estimated value. That's what we are looking for over here. Estimated value. And for the same person, you can go to the GP if you want to. Or rather than that one, you go to the 56th person and then for the research experience and then fill this in. See, since I started with the respondent 40, since I have already done that, so another way of getting this done, see, data go to 40, see, I'm going to call this one, see, the 40th one, and then see, that one I'm going to go put it up because I'm going to go to the 40th one, see, 40th of respondent. I'm not going to take into account the column, see, all the columns have been taken into account of this person, all the data, GRE score, CGPA, rate of recommendation, and then university ranking, everything will be into this one if you run this way. See, I call that one that 40. Then I'm going to put this one inside that research function, go to the that 40, and I'm going to say, hey, I'm going to narrow down that one to research. Another way to do that. Yeah, in the very beginning, you go to the research for the 40th person. Or you go to all the columns and then pick the one that you really need and then halfway through at the end of the day. Okay. Or you can go to this one, see, predict research regression. Because the 40th person, see, go to this one and then see, that's a, you know, that predicted value. You can go to the predicted value. Who's predicted value? 40th person's predicted value. See, you get the predicted value, all the y hats for all the individuals will be listed if you do the predicted. All the 400 respondents, predicted value y hat will be given in this one, research.predict. And I'm going to go to research.predict and say, hey, give me the value of the 40th person. Okay. See? Research regression, research predict. You don't have to go that one to that. Okay, you can simply, without putting back into that one, no, you can play with that one. Still, you're going to get the same answer. See? In the similar fashion, you can do this one, same thing for the, you can create a function for the, you already have created a function for what? CGPA, okay, GPA, CGPA, GRE, and then you can find in the several ways. The 40th one, okay, 40th one, the 40th one. Okay, simply if you can, if you want, you can use the one of the methods, okay, you don't have to go all these methods, but you can learn. Then go to the 56th one. If you keep to the 40th one for all these, okay. These are so many methods to get the same thing based on the research. This is based on the CGPA. I created a function, okay, based on CGPA. That function, see, regression, okay. Function, same way that you have based on GRE score. And this one based on GRE score, sorry. And then this one based on TOEFL score. I created a function in that way. Whenever I have any value, I can plug in into that one and evaluate based on the TOEFL value. What's the TOEFL value for that particular 40th person? So then I created my functions. So if you want the GPA, based on the GPA, you can go to the function and say, go to the data, go to the data 40th one. See, that 40th one. Sorry. Here, see, this one, based on this one. I simply go to the 40th respondent and then I select that what I want. Or I go to the data and then I select what I want, like this way or this way. Or I predict and I go to the 40th one. See, that all these produce the same thing. Go to this one and then I'm going to predict and then go to the 40th person and say, hey, give me the 40th person predicted value based on GPA. Similar fashion, GRE score. GRE function I created, go to the that 40. That 40 means the 40th person GRE score based on GRE score. For this way. Another way you can do it. I'm sorry. GRE or GRE fund. Okay, let's go ahead and see GRE fund. GRE fund. Yeah, it's GRE fund. GRE fund. Okay. GRE fund. Two of this way. So we go to the predicted value and then because these are the part of, you can go with the prediction because it's a part of the data. Similar fashion, see, data 56, and you're going to do the same thing for the 56 in a similar fashion. 56, one of the methods using, see, like this, 78%, 93%. Okay. Like that. In the Q7, for the best model that predict the outcome variable. Best model you can remember, best model. For the best model that predicts the outcome variable per degrees of used, see question 5. Edit the following equation. What is the best method? Best one is the CGPA. You can remember, see, chance of admit, see, of the ith person. See, YI, that's the same thing. See, chance of admit of the hat. I put the hat, okay. This is above this one the subscript, okay. This is the B naught, this one, see, that's the chance of admit. You have to plug in into those values. When you run the regression for the CGPA, that corresponding B0 and B1 will be plugging into here. So you got the best model as a best model. See, you get the best model. See, best model to explain the chance of admit. I'm going to go to hat of the ith person, B0 plus B1. Sorry. Erase this one. That's for the CGPA of the ith person. So chance of admit B0, CGPA, that those values are already calculated. See, CGPA, see, negative 1.0715 plus B1.20.2088 times CGPA of the ith person. The chance of admit at I. That's what we're expecting you to plug in those values. Or you can simply say y at for that particular y, negative 1.0715 plus 0.2088 xi. But make sure this x not gonna be same for the next one. But y gonna be the same, but x gonna change. Okay, next one GR. But out of all these, you can not like that. That's the one that we're expecting. And then that you make the prediction. Then if you go a little bit further down and write the equation y, you can now write this one, another chance of admit. Chance of admit, nothing but chance of admit hat plus other stuff. Okay. So chance of admit now you can write. So the ith person, this is ith person, other stuff for the ith person. Ith person is what? Negative 1.0715 plus 0.2088 CGPA I plus 0. Right like that, right like that. Maybe you want, or you can simply say yi equals negative 1.07 0.2088 xi plus here. Then we're gonna ask us to for the extra credit. They say to do the same thing for the 100%. Same thing. You know, if you want to do the respondent 40, 50, 60, 70, 80, 93, similar fashion you can find for the 100. 100 one, you don't have to do everything. You have to pick this guy only. Go to the 100 one and then undergraduate GP only. See, this entry only you need. See, and input the values for independent I100 into the equation you created. So that when you're gonna input the values, you should know the yi. You should know B0. You should not know B1. You should know XY. You know EI. That's kind of a discussion building up over here. So the data, I created the 100%. See, go to the 100%, all the entries. Then I really focus on my GP. That guy, see, his GP, 100% GPA. See, 100% CGPA is 0.7830. See, 100%. One oh one 0.79 is 0.79. We got what? 0.78. see, we go to data and then CGP, that 100. Why? Then see, chance of admit of the 100%, this one times 8.88. Is that 8.88? Did I? Yes, 8.88. 100%. This one, I'm sorry, this one. Oh yeah, CGPA. See, just look at for his CGPA. 8.88. It's 0.79. If you plug in into this one for here, you know B naught, you know B1, you know X is CGP. See, so the B naught of this one, see, is this one. See? So let's run this one, 0.78. Okay, I'm gonna run this one. See, CGPA regression B naught plus B1 of CGPA regression times data 100 CGPA, which is, I'm gonna look into this one, 0.78. 100%, this one, dead.cgpa. Is that right? Let me see. Yeah, they both give the same answer, right? See, see. If you multiply this by, see, go to the 100% CGP, which is 8.88. Go to that regression, it's B naught 0.28. Rather than doing by hand, I'm going to record or do by hand. See? Same thing. See? You can ask them to read it. See? B naught GPA regression, B naught, and then data of this one. That is same as you're going to run that one. See, CGPA. This one is same as this one. See, person. What is the function? Why function? Because the function has been built up by running regression. Okay. For the regression, I'm going to put this value only. See, this value. This means this value. I'm going to plug in into that one. I don't plug in, but I'm going to ask them to put this value input as an input to this guy. That input only enough. The rest has been already calculated. Only thing that different is from person to person is only from X. The rest would be the same from all the people. See, these are same. B naught and B1. I'm not talking about based on this one, based on the see, I'm sorry, this one, sorry, this one. See, based on this one. See, 4713. Is that what we have over here? 13, but 15 here. But because they based on what I saw, okay, but that's okay. 0713 here plus this one. See, and 2088. 2088. Or see 15 or 13. That's okay. See 2088. Was it 0715? But how come this one was? Okay, I'm gonna have a look at it this one more time. 15, no? 15. Okay, why here 15? Should be 15. It should be also 15. Okay, 78. Okay, let's run this one. 100%. I'm gonna go to 100%. I'm gonna say get his GPA and put it into the function. It's 7830. Okay, I run this one. 0.7830. I run this one. 0.78. See, almost like because I have rounded some parts I have rounded, okay, because the intermediate rounding are not allowed. We have to wait until otherwise, but it's closed, okay. See, or that see chance of admit to CGPA function go to see predicted value or estimated value. So admit for the 100 respondent. Can do that one like that way. See, R predicted chance of admit. See, GPA. Go to the GPA function. This one. See, 70. That's the same thing. That's the same thing. So you can do like that. See. And see, you can get the predicted value. See, with the predicted value. See, this one. 100% that one. That's the predicted value. So you can get the predict estimate calculate chance of admit for the 100%. Predict estimate calculate chance of admit for the 100 respondents. Sorry, 100 respondents. Predict GPA. This one GPA predict. Sorry, this one I'm gonna say GPA dot predict will give you that one too. This one. GPA predict for all of them. See, all of them. From that one, I'm gonna pick the 100%. See, and 101 is denoted like that. See, and narrow down. And then I'm gonna go to the actual one, observed one. See, that's a predicted R observed one, chance of admit. I'm gonna go to the data set. I'm gonna go to the 100%. I say, hey, give me the chance of admit, actual value. We know the actual value. We can read it, but if you have a huge data set, we're not gonna go ahead and read from the data. It's 0.79. Then you're gonna go ahead and find the difference between those two. Difference between those two cause the error. See, residual of the 100%. R observed chance of admit of the 100%, R predicted chance of admit on the 100%. See? That difference is given by residual of 100, see? Which is 0.006. Or you can go to this one, R observed chance of admit of the 100, you know, or GPA predict and 100. R observed one already have over here. You go to GPA predict and pick the 100% and then take the difference. So that's the same thing. Or you go to the receipt. Receipt using the receipt, you can get the residuals and you say, I need a 100% residual. I don't need everybody's residual. Even the 100% residual. You can get that from that way. You actually have the same thing. Okay. Then if you go ahead and put this one into this 0.79 observed value is 0.79. If you go ahead and plug in into this value with the error in this equation, plug in into this equation straight everything, both sides. You know the observed value, you know B naught, you know B1, you know the 100%, sorry, you know the 100% observed value, which is 0.79. You know B naught value, which is negative 1.0715. I'm going to plug in everything here. Okay, negative 1.75 plus B1 0.2088 times. You know the CGPA of that 100%. You know the error of that person. So they both left-hand side equals to right-hand side. See, I put the chance of observed chance of admit of the 100% is 0.79. The right-hand side is through the equation. See, this is B naught. This is B1. This is the 100% that GPA 8.88 plus the error. If you calculate this one, it is equals to 0.79 on this side. That means the equation satisfied. That's what we were expecting. Okay. So we input the value, those subscripted by I in the model equation. That means you have to input here, here, here. sorry, especially input the values, those in the model for independent 100%. 100%, 79 should come here, observed value. This is the estimated value. This part is the estimated value. This part is the error. That's what we expect. You can calculate it in different ways. Okay? So it's not hard. Okay? So you can learn many ways of getting this done, or just stick to one method. One method. Okay? Say observed value minus the predicted value. Observed value minus predicted value. You can recall accepted value. See 0.79. Let's do that. 0.79. Based on his CGPA. So observed value of chance of admit without taking into account other variables. Without. You're not going to take into account other variable. Only one variable being taken into account there, which is CGPA. With that one, see, whatever you have predicted one and the true one are very close. They are error incurred by estimating this particular the chance of admit or the y variable or the response variable is almost negligible. See, you saw that one. You already saw that one. 0.0006. So that's a good prediction. See, it's a good prediction. See, whatever observed value and the predicted value, we both fitting into lines into that particular this regression line. I think that's all we have. I think, do you guys have any question, anything you want to discuss? Anything on this one? And then you have that quiz also now. I made that one available, so you can access the quiz. Quiz is like a completely based on the chapter 8 review questions. We can go through that one tomorrow. We have plenty of time to talk about so many things. You see, mainly anything is that it's like a simple linear regression. Simple linear regression means like you can call that one actually. Simple means you have only one x. I pick this equation. I'm going to show to say this one. See, with the x, I go with this one. See, simple linear regression means this one. See, look at that. You have only one x. Simple. Linear means actually you're going to fit in, rather than fitting into regression line, linearization coming through that B0 and B1 has been given in this power 1 form, rather than giving the B0 square, B1 square like that. So, but simply, rather than go to that detailed way of that explaining this linearity, you can simply say this can be fitted into like a straight line. Let's say that you have a two of them, two variables. Then you're going to say B2, X2. This is in what? This is in 2 dimension. Then if you put another variable, it's going to be 3 dimension. The very moment that you're going to enter into a 3-dimensional form, what are you going to have? You're not going to have a straight line. Let's say that's it. You have a y, you have a B0 plus B1 X1, B2 X2, like a y hat. I'm interested in y hat. If it is y is nothing but B0 plus B1 X1 plus B2 X2 plus error. So this is the part I'm calling the y hat estimated part. See, they both are either categorical or it's a combination. Either these two would be the quantitative, or quantitative and categorical. Doesn't matter, or categorical and categorical. But mainly, let's say that doesn't matter. Based on that one, if you have that line, if you draw this one, you're going to have this one here, X1, Another one, see, you can have your x2, see, degrees 90 degrees, see, like that. Same y response, y will be over here. Then what are you going to have? You're not going to have a straight line. You're going to have what? Plane. 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 It's a hyperplane. Hyperplane equation. See, of the hyperplane is what y hat equals 3 naught plus 3 plus b2x2. That's the regression equation. Then you can have what? Multiple linear regression. Multiple linear regression. Multiple linear regression. Earlier we have simple linear regression. Simple means one variable. Multiple means multiple. You see x1 and x2. See, this one simple linear regression. That's the one that simple linear regression. When it comes to the multiple linear regression, then you're going to learn down the road. There are severe vector problems that emerged because rather than this guy interacting with this one, these two also try to interact with each other. That will create a problem. These two, rather than independently interacting with these two separately or independently with this guy, they both try to interact with each other and then try to create another variable called the interaction term plus x1 times x2. You can add that one to interact. Let's say this guy is the major one. Major one we call the exposure variable. This is called the response variable. This is exposure. These are called some kind of a control variables. I'm going to add another variable like a control variable. We're going to see whether this control variable is going to be an interact, effect modifier, or confound. Confounded means like a secretly that having like that association with this one and effect to the final results. That's called the confounding. And lurking and hidden latent variable. It can be either confound, effect modifier, or it can be a interactor, the third one. So that kind of a broader discussion you're going to build up in like especially in a 620, 625, one for the quantitative variable, the other one for the categorical variable. See that this kind of a correlation built in up between these two are called the multicollinearity. Those two should be done later on. If you keep adding more variables, that this equation becomes very unstable. For the sake of that, adding that on, the more variables you add, the far better that your model would be. That doesn't mean that will give you that perfect model at the end of the day, because it has other drawbacks come along with that one. See, so those are to be that address at the end of the day. So that's why we're not going to add more variable to keep the elegance and the rigor of this one. We normally that add several variables and then look for the unnecessary variable by certain procedures. We're going to weed out. If you have extra ones, weed out. Or you systematically add one at a time. Forward selection, backward elimination, stepwise. So many methods will be introduced to down the road. Okay. But we're not going to talk about that in broad range in this class. But at a certain point, we're going to talk about multiple regression in another, I think, next homework, if I'm right. But anyhow, related to this homework, any question, anything, if you have. If not, we can wind up here and then meet tomorrow and then continue our discussion. If
Yeah, that sounds good.
Okay, perfect.
Everything's good. Okay, then let's meet tomorrow, and then I'm gonna let you go, and then you can get started working on this one. Have a good night. See you
Have a
tomorrow.
good night.
Good
You
night.
too. Have a good night.
Good
Thank you.
night.
Good night. Thank you very much.
All right.
Good night.
Have a good night.
Thank you. Have a good night. Thank you very much. Thank you.